All right. We're looking at section 4.6 where we're going to perform operations with complex numbers. Now, to this point, we've only dealt with real number situations. Today, we're going to introduce and work on problems with deals with complex numbers. Now, complex numbers deal with imaginary numbers. Imaginary numbers means we're going to introduce a new variable into our number system, which is the value I. If you look at the value I, it has a value attached to it, which means I equals the square root of -1. Now, if you remember in previous lessons in different sections of our book, we never had an answer that had a negative inside the square root. We were always said it was no solution. Well, no solution meant no real solutions, but we do in fact have a solution. It's just an imaginary number. So I means it's the square root of the -1, which means that if you look here, I squared just equals -1. So anytime you square the number, you just write what's inside the square root and get rid of the square root. So some of the examples that I have here, if you look on this first one, it says the square root of -r. Basically, if you were to reduce that, it means you're going to have the negative, which means, oh, that's I, so you get rid of it and put it on the outside of the square root, and you have I times it by the square root of r. If you look at the second portion right there, you have I times by the square root of r, and the whole thing is squared. Well, essentially what you're going to have here is I squared times it by the square root of r squared. Well, I gives us the -1, and the square root of r squared gives us r, which then that gives us the value of -r. So we're going to solve some problems that are going to give us imaginary numbers. The first example here is -5x squared plus 17 equals 62. So the first thing I'm going to do is subtract 17 from both sides. Now I'm going to have -5x squared on the left-hand side, and I'm going to have 45 on the right-hand side. Divide everything by -5, which gives me x squared equals a -9. Well, I'm going to take the square root of this, which the square root of x squared is just x, but I have a negative inside my square root, so that's going to give me the imaginary number. But the square root of 9 gives us 3, but because you place the square root in there, it's going to be plus or minus 3, and we're going to have 3i. So that would be the value for x. If you look at b, it has 6x squared minus 19 equals -67. First thing you're going to do is add 19 to both sides. So now I have 6x squared equals, that would be what, -48. Divide everything by 6. So now I got x squared equals a -8. So going through the process, we know that if I were to take the square root of both sides, we'd have negative, so we know it's going to be dealt using the value of I. But if I go over here and just say this is the square root of x squared gives us x, it's going to equal, I'm just going to take out the negative, and I'm going to put I to the outside and have the square root of 8. But the square root of 8 can be simplified. We know that it's the square root of 4 times 2. 4 is the perfect square number. The square root of 4 is 2, so your answer for this is going to be plus or minus 2i times by the square root of 2. Okay? Now, sometimes complex numbers can be also have some real number values in it as well. So complex numbers can be written as a plus bi. So this is considered standard form when you're dealing with values that have some complex numbers in it. All right, if you look at the statement below, it says that I holds the same properties as variables when using operations to solve or simplify, except when you see I squared. You can change that to -1. So everything stays the same. You can kind of treat I just like a variable X, Y, Z, stuff like that. So when you're adding and subtracting, you can only combine like terms. So you can only combine imaginary numbers with the same imaginary numbers. When you multiply, you're going to distribute and add the powers just like you would do with any other variable. The only thing that would change is when you divide, it says you must multiply by I or the conjugate because you cannot end up with I in the denominator. Reason for that is I is essentially a square root value, and you can't have square roots in the denominator. So I'm going to show you some examples to help you solve or simplify those particular expressions. So for these examples here, we're going to be asked to simplify the expression, write the answer in standard form. So standard form, remember, is that a plus b times I. So it's an addition problem. So essentially what you're going to do is you're going to write -7 plus 4i, and since it's a plus, you're going to write it the second parenthesis as is, so it's going to be plus 12 minus 5i, and then you're just going to combine like terms. So the real numbers solutions are -7 and 12. If I combined those values together, I would get +5. Cross those out. And here I have my imaginary numbers of 4i and -5i. So it's going to be -i. So 5 minus I would be my answer for that particular expression. If you look at example B, you have 6i minus the quantity of 17i minus 10. So what you're actually doing is you're taking this 6i and then you're just changing the signs of everything inside the parentheses because you got the minus there. So it's going to be minus 17i plus 10. So I have just the one real number term. So I got 10, and then 6i minus 17i is going to give us minus 11i. Okay. Looking at C, C is we have to distribute. So we're going to distribute here and we're going to distribute here. So again, you're just going to treat the I just like a variable when you're distributing. So I go over here, -12i times by 5 is going to give me -60i. -12i times by 4i is going to be, well, negative times a negative gives us a negative. And 12 times 4 gives us 48, and I times I is I squared. Okay, but I squared, they said, was -1, so I'm going to change that back to -1, so I'm going to have -60i minus 48 times it by -1. Well, -48 times by -1 is a +41, so now I just have to write it back in standard form. So I'm going to have 48 minus 60i. Okay. Next, part D, it's multiplication. We're multiplying two binomials essentially together, and we have to FOIL it out. So we have -3 times 2, which is -6. -3 times a positive 6i, which is -18i. -5i times 2, which is -10i. And then finally, -5i times it by positive 6i gives us a -30i squared. Okay? I squared, just like in part C, we're going to change that back into -1. So I get -6 minus 18i minus 10i minus 30, and it gets multiplied by a negative 1. Well, I change that. That's going to be, I'm going to make that positive. So now I just get to combine the like terms. Keep it in standard form. My real number solutions are negative 6 and positive 30. Negative 6 plus 30 gives us a positive 24. And then our imaginary solutions, we got negative 18 minus 10i, which gives us a minus 28i. Okay? All right, let's take a look at example E. Now, example E talks about what we looked at the top, where it says we can't have I in the denominator. So when you have a singular term of just like 8i, all you have to do is get rid of the square root. So in this case, the square root is I, so you're going to multiply both the top and the bottom by I. Now, the bottom gives us 8i times I, which is going to give us 8i squared. And then you're going to distribute the I over the negative 24 minus 48i, so I get negative 24i minus 48i squared. Now remember, the I squared for both of these is going to be a negative 1, so I'm going to say that's going to be negative 24i, and then negative 48 times by negative 1 is a positive 48, and it's going to be all divided by 8 times the negative 1, which is going to give me the negative 8. And I can simplify this because 48 divided by negative 8 is going to give me a negative 6. So that's my real number solution. And then negative 24i divided by negative 8 is going to give me a positive 3i. All right. Now F is a little bit different because you have an operation of addition or subtraction in between a real number solution and an imaginary solution. So in this particular situation, we're going to have to multiply both the top and the bottom by the conjugate. The conjugate basically means is you're going to keep the same values of negative 4 and I, but since the original denominator had subtraction, you're going to put addition. So that's what the conjugate means. So that means you're going to get rid of any imaginary numbers in the denominator while doing that. So if you were to FOIL out the denominator is going to give us negative 4 times negative 4, which gives us a positive 16, and then it's going to be minus, and then I times I is going to give me I squared, which we know that I squared is negative 1, so that's going to give me 16 minus the negative 1, which is 16 plus 1. Now if I look at the numerator is different, but we're just going to FOIL it out. So 8 times negative 4 is a negative 32. 8 times I is plus 8i. I times negative 4 is minus 4i. And then I times I is plus I squared. Well, again, we know that I squared is negative 1. So when I combine that, I'm going to have it as negative 33, because negative 32 plus a negative 1 is negative 33. And then when I combined 8i and 4i, I get 4i on the top, and it's all divided by 17. Okay. If we look at the next page, you can plot complex numbers. Now, the graph we have on the right here, we known for a while is an XY coordinate plane. Well, when you're dealing with real numbers and complex numbers, anything that's on the x-axis, so to speak, is considered any real numbers, and anything on the y-axis is considered to be imaginary numbers. So if you have something like 3 minus 2i, that's like the ordered pair 3 comma negative 2. So then you just plot that point. So you go 3 in the real numbers section, negative 2 in the imaginary, and then you just plot the point. So that's 3 minus 2i. If you look at negative 2 plus 4i, so that means the real number negative 2 is going to the left, the imaginary is going up 4, so I got negative 2, and then 1, 2, 3, 4. So I got negative 2 plus 4i. 3i, you're not going anywhere in the real number sense, so basically it's 0, so you're only going imaginary up 3 units, so this is where 3i is located. Then finally, negative 4 minus 3i is you're going to go left 4 units and then down 3 units, so 1, 2, 3. So this is our points, negative 4 minus 3 times I. And then the final thing we're going to take a look at is absolute value of complex numbers. Anytime you have a complex number in standard form a plus bi, to try to find the absolute value of that number, all you're going to do is take the square root of whatever the values of a squared plus b squared. So if you look at example A, we have 4 minus I, where a equals 4 and b equals a negative 1. So you're just going to plug those into this formula here. So it's going to equal the square root of 4 squared plus negative 1 squared. 4 squared is 16. Negative 1 squared is 1, which then gives us a square root of 17. If I look at b, negative 3 minus 4i, a in this case is negative 3, b in this case is negative 4. So then we're going to solve it accordingly. It's going to be the square root of negative 3 squared plus negative 4 squared. Take the square root. Negative 3 squared is going to give me a positive 9. Negative 4 squared is going to be a positive 16. When I add those together, I get the square root of 25. Well, the square root of 25 is 5. Looking at C, I have 2 plus 5i. Well, again, A is 2. B is 5. So I got the square root of 2 squared plus 5 squared. So 2 squared gives us 4. 5 squared gives us 25. Add them together, I get the square root of 29. I can't simplify that any further. If you want to give it a decimal approximation, you could. And then finally, D is negative 4i, which means A is 0 and B is negative 4. So if you wanted to put A in there, you could say 0 squared plus negative 4 squared, which then would be 0 plus 16, which would be the square root of 16, which then would just be 4. And that is being able to perform operations using complex numbers. Hope this helps. Until next time.